This is the solution for the problem parallel courses do. It's labeled hard and it's actually very fun to do. It is hard because it involves a number of concepts and they can be complicated to put together. I'll be attempting to explain all of it with the help of a couple of diagrams and very interesting test case. First, let's talk about the problem itself. You're given three pieces of information, n, relations, and k. N specifies the number of nodes in the question. Number of, and by the way, nodes are equivalent to courses in this case. So n specifies the number of courses. From 1 to n, there will be n number of courses. Relations specify what the graph layout is. In a case like this, relations would mention 2 to 1, 3 to 1, 1 to 4, like so. Then we have k at the very end, which in my opinion is what makes this problem really interesting because it limits the amount of courses you can consider in one iteration, in one time frame, or in one semester. These courses or these nodes have dependencies. As you can see, the course 1 or the node 1 has a dependency on course 2 or node 2. Without having 2 completed, you can't take 1. Without having 2 and 3 both completed, you can't take 1 actually. If 2 is completed, that's fine. 3 is completed, that's fine. Only after that, you can take the course 1. Fine? Cool. So, what now? Where does the K come in play? K sort of restricts you to select how many courses you can have. In a case like this, you can say that for K equals to 2 and relations given like this, and number of nodes is 5, as you can see here. How do you go about this case? See, k equals to 2 means that of these three available nodes, all of these three courses that have no prerequisites, you can take any of the two. Let's say 2 and 3, for example. In the next iteration, the only nodes remaining are 4, 1, and 5. 2 and 3 have already been considered. What do you do then? Again, the only course that's left without having any dependency is the course 4. So you'll take the course 4 as well. Now all of these three have been completed by the second iteration. First iteration was 2, 3. Second iteration was 4. Third iteration, 1 is now available. And you can take 1. And then in the fourth iteration, you can take the course 5. Taking a total of 4 iterations like so. Now, this, by the way, both of these may give you a wrong impression of K because K looks like just limiting factor and it looks like a problem of topological sort. That would have been very easy, but that's not the case. I'll tell you one very, very good test case which will destroy your assumptions on this. By the way, this is the graph layout of previous course to next course, and this is how you can generate a graph. I want you to pause the video right now, and for k equals to 2, can you tell me how many iterations would it take to complete all of the courses here? Pause the video right now, and I'll explain the solution very simply. Cool. So let's explain the solution, and this is what we have here. We have a graph layout like this, and I've labeled semesters 1 to 6 here, enclosed in circles. Each circle is of one semester. So in this case, we had what? We had 4 courses available for you to be taken. You take any 2 of these 4 since k equals to 2. Let's say that you decide to take these 2. Since both of these 2 are completed, this node gets unlocked. And since these 3 are now available, you can pick any of these 2. In this case, I picked both of these. Then third semester, I picked this, 4th, 5th, and 6th. Pretty easy. But what if we had a case like this instead? Look at this. Just by changing the ordering of these nodes, k remains the same, the graph remains the same, but just by changing the ordering, I was able to get a different, smaller answer. First semester, I take the same courses, but in second semester, instead of taking both of these, I take the bottom 2. In the third semester, that allows me to take this node, and then the fourth and the fifth. The problem becomes insanely simpler now. See, In the earlier case, we had to take 6 semesters to complete it. Now we have to take just 5. Interesting, right? So it's clear that the selection of what K you select is going to be crucial to select to get the minimum possible answer. Cool. Now let's discuss what data structures are we using and how do we actually go about implementing this. So implementation level details, let's talk about the data structures graph. Graph is obviously this kind of structure that we need to have in place. 2 goes to 1, 3 to 1, 4 to 1, and 1 to 5. We have to store this information in a graph. So we'll have self.graph. I'll make a default dict containing list. So each node can have multiple children. In this case, it only has one. All of these nodes only have one children, but they can have multiple children. So we need to keep a list. We also need to know the in degrees. Now in degrees are what makes it easier for us while implementing and say that, okay, all of these 3 nodes have in degrees 0 in the first iteration. Let's take this example, which would be better. All of these 2 have in degree 0 in the first iteration. We can consider both of them. Then one would get unlocked since both of these nodes have been taken already. So we can reduce this guy's in degree by 1 here and then by 1 here again. This would make its in degree 0 and thus be available to be taken. Cool. We need to store in degrees. And we'll do this self.n. By the way, let's store k and n here. Cool. Now in degrees is going to store how many nodes have, or what particular node has what number of incoming edges. Pretty simple. Let's actually build that graph because it's currently an empty list. It's a dictionary of empty lists. So we'll have previous course, comma next course, in what? In relations. And we're going to say in degrees of the next course plus equals to 1. So 2 comma 1, a pair like this comes in, and we'll say that for 1, the in degree has to be increased by 1 because 2 is going into 1. Cool. We also need to know that the graph of this particular node of previous node has a child next course. Cool. This will generate the entire graph for us. There's one small implementation level detail you want to very much take care of is the negative ones here, because the question gives you all the inputs as 1 indexed. We want to make it 0 indexed. Cool. Now all of these data structures have been taken for care. We're set with the data structures. By the way, I have made in degrees as self.in degrees. I'll come to it very soon. First, let's now talk about the nodes themselves. Now each nodes have either they have been taken or they haven't been taken. This is sort of the general classification. In a state 0, when we're just starting, none of these nodes have been taken, so we'll mark them with 0. So not taken means 1. So we'll mark all of these nodes as 1. None of these have been taken. In the first iteration, when we'll take 2 and 3, we'll mark both of these 0. The only remaining ones would be on 1 here and 4 here. And that's fine, and we'll continue doing this. So again, the classification for nodes is either it's taken or it's not taken. If it's taken, then we'll make it 0. If it's not taken, we'll make it 1. This is a simple binary classification, and so 0 and 1 makes sense. There's one last thing you need to know. See, we want to be able to represent what the layout of the graph is at an instant. Because when we are looking at a recursive solution, which I'll come to very soon, we need to be able to look at, say, a simple string and say that, okay, I know for a fact that all of these particular nodes have been taken into account and all of these nodes haven't been taken into account. We need a very compressed manner of representing which nodes have been taken and which haven't been taken. We'll call it a mask. And this is where the concept of bit mask comes in. And it says that Um, okay, I'll give you an example. For example, 1101. If a mask like this comes in, it means that this node hasn't been taken, so not taken as 1, which means the index 0 hasn't been taken, the index 2 hasn't been taken, and the index 3 hasn't been taken. These indices themselves can represent nodes, saying that the node 0 hasn't been accessed, the node 2 hasn't been accessed, and node 3 hasn't been accessed. Simple? Makes sense? We have sort of compressed this representation of graph into one single value. This is what we'll call the mask. And we'll initialize it to saying that none of these values have been accessed yet. So all of them are ones now. So we'll do self.n minus 1. Make sure to put the brackets like this here. Otherwise it'll screw up your entire thing. Cool. So we have mask in place saying that all of these bits are 1 now. All of these nodes have not been taken yet. Cool. We also need in degrees in place and we already have that. And now I'll do one small thing. Bear with me. We'll create a recursive function. And to the recursive function, we'll send the mask and the in degrees. We'll actually send this as a tuple for implementation purposes. And this will complete this function right here. Cool. Why do we do this? I'll get to it very soon. First, let's create this function. Recurse self, comma, mask, comma, in degree. We'll call it in degrees here. Now, what's the base case of recursion? I'll come to why we need recursion in a second, but think about it in a recursive manner. And why would we need base case for recursion? Why would we need recursion at all? I'll come to explain very soon. But what's the base case of recursion? Was the point where we can say that this graph has been completed, this problem has been solved. It's when the mask is 0. If not mask, then return 0. Pretty simple. Okay, but why do we need recursion at all? See, we need recursion because every time we make a decision of the given list of nodes, of the given list of n nodes, or let's say m nodes, we want to only select k of them. And each such combination could then be split out into their own trees. Each of those trees themselves which will have again another set of decisions they'll take, and so on and so forth. They'll continue till the very end. This is why recursion is very helpful. You can simulate what's going to happen in the future and just take whatever the answer they give and take the minimum of them and return that. So I'll return the answer here. And because answer is supposed to be minimum, we'll just do float of infinity here. And in something, we'll do something here that will reduce the answer for us. First, we need to know what nodes are available to be taken. Now, what are these available nodes? Obviously, the nodes that have been taken already, the nodes which are 0 are of no use to us. So we want nodes which are which have the value 1. So we'll say I for I in say range of self.n. We want to iterate over all the bits and say that if mask and 1 shifted by I. If that is true, if the current ith bit is set, then that node is ready to be taken. That node hasn't been considered yet, so in the second iteration, it would be nodes like 1 and 4 that haven't been considered yet, or in this case 0 and 3 because we'll shifted everything by 1. And we'll say that, okay, these two nodes haven't been taken yet, so they have the value 1s. Both of these will have the value 0 in the second iteration. But there's one more thing we need to know. Even though both 1 and 4 are not yet taken, which are 1s, only 1 is actually available because it's in degree 0 because 2 and 3 have already been taken. And so we'll write and in degrees. I'll make it like this. Cool. And we'll say in degrees of this current node is 0. This will get me a list of all the possible nodes that I need to consider at this moment. Of course, they could be a very long list and we only need k of them. So let's say for a particular combination, giving me k nodes in combinations of nodes comma k will do something, and I'll actually put it here. Combinations, by the way, is from itertools, import combinations. Good. This will give me all the combinations. So it's NCR basically, but with list. And of this list, select me k elements and give me them. One small implementation level detail again is that what if the number of nodes is less than k? What if k was 5 here and we only have 2 nodes available in the 0th iteration or in the first iteration? In that case, you still want to pass them, both of them, right? But 2C5 would give you a value of 0. You actually wanted to return 2. So let's not keep it k here, but the minimum of k, comma, minimum of length of nodes. So if k is still 5, but number of nodes is 2, we'll select 2 out of 2. Length of nodes would be 2, and we'll select this. Fine. Okay, we were getting very close to the solution. Okay, what do we do once we have selected those k nodes? Once we have selected those k nodes, let's iterate over them for node and k nodes. What do? We want to take whatever mask we had right now, whatever in degrees we had right now, and edit them, update them with new values, which we think are going to be the answer. Let's call it new mask and new in degrees. And what will they be? This is going to be mask itself, and well, remember that in degrees is actually a list. Sorry, it's a tuple, and we'll convert it into a list just for easier handling. So we'll say, okay, this is fine. Once we have gotten the new mask, what do we do? In the new mask, we want to update the information that I've taken these k nodes. I've taken these k courses. So whatever these had contributions in mask, remove them. How do we do that? In new mask, I want you to somehow remove the contribution of this particular node, which we can access like this. How do we make it 0 though? This is where bitwise operator comes in. Another bitwise operator comes in, XOR. And we'll just XOR it with this value. Why? Because we know for a fact that the bit is set. The bit was already set here. And this is what we have gotten up till now. And so we can just XOR it with this value again, which will unset the bit, and we'll have the new mask ready. Cool. What do we do after we've gotten the new mask? Let's have answer equals to minimum of answer, comma, 1 plus self dot recurs. So each step is sort of taking one cost at the very end, and that's what we'll consider. What do we send in? We'll send in the new mask and the in degrees. Not just any in degrees, but the new in degrees. We also need to update the in degrees. How do we do that? See, this is where this guy comes into play. We have the information of how all of these nodes are related, and we kept it independent from in degrees just because of this reason. We can access this guy right here, self graph, and we can access the current node we want to account for. We'll say for child in this guy, this will get you a list of all the children. And for all of these children, what do we do now? Everything should come together. We'll reduce its in degrees by 1. So we'll say in degrees of child minus equals to 1. Not just any in degrees, but the new in degrees. And I think this should do it. Let's do a sanity check. So as you can see, this is a fairly complicated program. DE. default date. And it requires a lot of concepts like bit masks, recursions, and then we'll do dynamic programming in a bit. And then the knowledge of how in edges work and things like that. It's a pretty good question. And it has the worst acceptance ratio submit to acceptance just because of this reason. I did a spell mistake. Previous course. Cool. Okay, what else? We also need to send in the tuple here. K is not defined, right? K is not defined because it's self.k. Cool. Okay, lots of errors. It's a good problem. Cool. Accepted. I wanted to run on all the sample test cases, but before that, let's just do caching. LRU cache none. This will specify that have a cache as big as how you want. That will increase a lot of these times of this guy because it's again recursive. Cool. Instead of that, I'm fairly confident it'll work. So let's just submit this. There you go. This works. So this is the solution for the problem parallel courses too. It's a decent problem, and if you want a written version of it, I have my write-up up here. I'll link to it in the description. Feel free to go over this code again. Again, it's mentioned in the write-up as well. Copy paste if you want, experiment and play around. There are little things like this guy we have done. Things which can make it look complicated, but it's actually simple once you understand it. And I think this test case should really bring forward the much importance of K and selecting the right nodes of any combination. Anyway, that's all from my side. If you found this video helpful, please like it because that gives me valuable feedback. If you have any more feedback, I'm always there in the comment section below. Have fun.